So hello everyone and welcome back to a brand new video, and in this video I'll be solving problem C, that is Koxia and number theory from the goodbye round. So let's move on to the video and see how we can solve this. But before we move on to the solution, I want to tell you guys about Newton School's coding contest. As you guys know, Newton Schools does this coding contest every month, and this month the name of the contest is Code Rush X, and the prizes are better than ever before. So you can win prizes up to rupees 10 lakhs, and along with this you can win placement opportunities in top product companies. So like if you guys want to play this for fun or you guys want to play this for placements, that is totally up to you. The contest will be on 28th of January. It will start around 9 p.m. and the contest will be 3 hours long. So there will be ample amount of time for you guys to brainstorm and solve good quality problems. So if you guys want to benchmark yourself or just win some placements, this is a very good opportunity. I will leave a link to this contest in the comments and in the description, so you guys can go and sign up from there and show, or you can flex how good you are at problem solving. So now let's move on to the solution. So in the problem, we have been given an array of size n, where n can be up to 100, right? So something like a1, a2, a3, so on up to an. And we want to answer in either yes or no, right? If such a positive integer x exists, that like if we choose any pair, right? So for any pair I and j, GCD of ai plus x and aj plus x should be equal to 1. So no matter what pair you choose, GCD of ai plus x and GCD of aj plus x should be equal to 1. And we have to answer in either yes or no if we can find such a positive integer x, right? If such a x is possible. So let's see how we can solve this. Right, so first of all, let's see a very obvious case where the answer will be impossible, right? So consider that you have some element ai which is equal to aj, which is equal to some value, let's say k, right? So you have two equal elements. In this case, no matter what value of x you choose, right, GCD of ai plus x and GCD of aj plus x will just be equal to GCD of k plus x comma k plus x, which is equal to k plus x itself, right? So in this case, no matter like what value of x you choose, your GCD will always come out equal to k plus x, which is obviously greater than 1. So in this case, answer will be impossible. So this is the very first obvious case, right? So if you have any two equal elements, answer is impossible, right? So that is the first case. Now let's see how we can move forward. Like if all the elements are different, now how can we solve for that now? So you want to choose some value x such that GCD of ai plus x and GCD of aj plus x is equal to 1, right? Let's rewrite this. Let's say your ai plus x is ai dash and your aj plus x is aj dash, right? So we can say your GCD of ai dash comma aj dash is equal to 1. But we can rephrase this and we can say that like if for every pair your GCD of ai dash and aj dash is equal to 1, then it means that for any prime p, it can divide at most one element, right? It can divide at most one element. For example, if we have, let's say, ai dash is equal to k1p and if your aj dash is equal to k2p, then if you find the GCD of these will come out to be at least p, right? So that will violate our condition. So for any prime p, it can divide at most one element. So like if your ai dash is a multiple of p, then your aj dash cannot be a multiple of p. So you can say that your new goal is for any prime p it should only have one multiple. Or in a more formal way, you can say that for any prime p, there can be at most one index I such that ai dash modulo p should be equal to 0, right? So there can be at most one index such that ai dash modulo p is equal to 0. So that is our goal, and now we have to check like if we can achieve this for every prime p or not, right? So now we can iterate over every prime p. So for every prime p, we have to check if we can achieve this goal or not. Now how can we check this? So to check this, we can maintain an array that stores frequency of modulos, right? What I mean is, for every prime p, you can make a frequency array of size p. So first is 0, 1, 2, 3, 4, so on up to p minus 1. You can store the frequency of modulos in this one, right? What I mean is, you can iterate over your array A. So we have A1, A2, A3, so on up to AN. You can find the value of A1 modulo P. Let's say A1 modulo P is equal to 2. So initially the entire array will contain 0, right? Frequency of every like modulo is 0. Let's say A1 modulo P is equal to 2. Then you can increment the frequency of 2. So 2 becomes 1 here. Let's say you calculate A2 modulo P again. A2 modulo P, let's say, comes out to be 4. Then you can increment 4 here. Let's say you found A3 modulo P. Let's say A3 modulo P came out to be 2 again. So you will again increment 2. So now 2 becomes 2. Similarly, you can iterate over all the elements from A1 to AN and generate this frequency array. Sum of all the elements, right? Sum of all elements in this will be equal to n, right? Because we have n elements and for every element we are incrementing one time. So sum of all the elements or all the frequencies should be equal to n. In the end, you will get some array, right? Something like this. After iterating through all the elements, you will get some array like this. Let's say 2, 5, 4, 1, 0, 3, so on up to, let's say, 3 again, right? So this is 0, 1, 2, 3, so on up to p minus 1. And our goal is that we want to like only have one index such that ai dash modulo p is equal to 0. But if you check here, right, if you check here, there are two elements such that ai dash modulo p is equal to 0, right? So we need to kind of shift this array, right? And to shift this, we can add x to this. We only want 0 or 1 elements on the first index, right? Because we only want at most one element that can be a multiple of p. So what you can do is you can shift this array, right? So we can add some value x, right, and shift this array. Let's say I want to like have this 1, add this 0. So I can shift this array p minus 3 times. So if I shift this, it will look something like this. After shifting, it will look like 103 and whatever, right? This was my frequency array. This was frequency array for my initial array A, and this is my frequency array for my changed array A dash, right? When I added x to the array, this is my new array A dash, and this is the new frequency table for p. As you can see, here we had two indexes such that ai dash modulo p is equal to 0. But now that we have added x to this, here my value of x is equal to p minus 3. Now I have shifted the array, and in my new array, now there is only one element who has ai dash modulo p equal to 0. There is only one such element, right? So this satisfies our goal. So you can say that your value of x modulo p is equal to p minus 3, right? So this is the first equation that we get. And similarly, you can find the value of x for all other like primes, and you can find the value of x using CRT, right? Let's say we have 5 primes, p1, p2, p3, p4 and p5. You will find the value of x modulo p1 is equal to, let's say, x1, x mod p2 is, let's say, x2, and so on. X mod p5 is equal to x5. Then we can use Chinese remainder theorem to find the value of x here, and it is guaranteed that value of x will always exist. So that is kind of the solution, but there can be a problem here, right? In this frequency table, we were able to find this value 1, right? What I mean is, in this frequency table, we have 2, 5, 4, 1, 0, 3, so on up to this, right? In this frequency table, we were able to find an element where frequency was less than or equal to 1. So we chose the value of x such that this one came to the beginning. But what if all the frequencies are greater than 1, right? We can have a frequency table, something like this. Let's say we have 2, 3, 4, so on up to, let's say, we end at 2 again. In this table, if all the frequencies are greater than 1, then no matter what shift you apply, right? Let's say we apply some random shift x. If this is your frequency table for A, you generate the new frequency table for A dash, then it is guaranteed that the new element in like A dash will also have frequency greater than 1 at the beginning, right? So in this case, you cannot achieve your goal, right? A1 like AI dash modulo p equal to 0 is not possible for only one index, right? Number of index will be greater than 1 in this case. So if all your frequencies in your frequency table are greater than or equal to 2, then you can say that your answer is impossible again. So that is the second condition that we get now, right? So I can again draw out a table for this. So let's start the problem. The very first case is case 1, that is if any two elements are equal, then the answer is impossible. Otherwise, we have case 2, generate frequency table for every prime p, right? And find some value k belonging from 0 up to p minus 1 such that frequency of k is less than or equal to 1, right? And apply k minus p shifts, or you can say that you get a new equation, and your equation says x modulo p should be equal to k minus p, right? Or you get a new value, or you get a new equation for x. But like if no such k exists, then the answer is impossible. Otherwise, using CRT, we can solve. Using CRT, we can solve all the equations. And get the value of x. In this case, answer is possible. Right? But still, there is a very big problem with this, and the problem is the time complexity, right? What we are doing is we are iterating over all primes. And then finding the frequency array, right? So to find the frequency array, it takes us O of n time and like to iterate over all the primes, it will take us O of p time, right? But in this case, my AI can go up to 10 to the power 18. So my P is also very large. My my P is also around, you can say like 10 to the power 15 or something, right? Like this is a very generous estimate, right? Like if your AI is up to 10 to the power 18, your P is also around in that range. But let's assume your P is up to 10 to the power 15. So in total, my complexity is O of P into N. And as my P is around 10 to the power 15, this is obviously not possible, right? This is obviously not possible. So to optimize this, we can make use of pigeonhole principle, right? What that means is that we know that if we have a frequency array, right? If we have a frequency array, then sum of all the frequencies should be equal to n, right? So let's say we choose some prime p such that p is greater than n by 2. And if all the elements are 2 in this frequency array, then my sum will be equal to p into 2, or you can say it will be greater than n by 2 into 2, or it will be greater than n, right? If your sum is equal to p by 2, and if your p is greater than n by 2, then your sum will also be greater than n by 2 into 2, that is your sum will be greater than n, which is not possible, right? So if your p is greater than n by 2, then at least one of the elements will be less than equal to 1, right? So that is the condition that we can use. So for any prime p which is greater than n by 2, we don't need to check for it, right? Because at least one of the elements will be equal to 1. So in this case, we will always be able to form the equation. We don't need to check for the impossible condition in this case, right? So we can optimize our time complexity from p to n by 2, right? So it becomes O of n by 2 into n, which is O of n square. And as our n is up to 100, right, this will easily work. So that is the entire solution. So I will like summarize it once again. So first of all, you can check if two elements are equal or not. If they are, then the answer is impossible. Sorry, it should be impossible here, not possible. Answer is impossible. Otherwise, we generate the frequency array for every prime p, and according to pigeonhole principle, we only need to consider primes up to n by 2. Then check if there is some frequency k less than or equal to 1. If there is, we can generate an equation and solve it using like CRT. Otherwise, if there is no such k, then the answer is impossible. So that is the entire solution. And if you guys want to see the code for this, here is the code. So I will sort my array and I will check if there are two equal elements or not. If there are, then the answer is false. Otherwise, I will generate all the primes up to n by 2. Here I am assuming n by 2 is equal to 60, right? Because my n is 100. So generating primes up to 60 is enough. So I will generate primes up to 60. Then I will iterate over all the primes and keep a frequency array. So I will keep increasing the frequency, and in the end I will check if there is some index k where value is less than or equal to 1 or not, right? So if there is not, then the answer is false. Otherwise, I can return true at the end after checking all the primes. So that is the entire solution. And if you guys have any doubts, feel free to ask in the comments or join my Discord server. I'll be more than happy to answer your doubts there. And I will see you guys in the next one. Bye bye.